And now I will invite
Thanks very much for having me.
Katharine to come in from backstage, and she will introduce the panelists, but I get to introduce Katharine. I'm so pleased that she accepted my invitation to chair this panel. Katharine got her PhD in the notoriously famous Optoelectronics Research Center at the University of Southampton. It's produced stars like Katharine and others. And then she's really spent much of her career in industry in the last decade or so at Facebook and Meta, where I tended to talk to her to get feedback on some important questions about where fiber optic technology would apply and what sort of choices were needed. She now has her own sort of optical consulting company, Arabelle Systems, and she holds an appointment at another university famous for its optical research, and that's University of California at Santa Barbara, UCSB. So it is my absolute pleasure to have Katharine join us to moderate the panel, and you can see that she has put together a star-studded panel. So Katharine, the floor is yours, and I will put on your slides.
Yes, well, thank you very much, Dan. And welcome everyone to the panel this afternoon. This is going to be a lot of fun. I was backstage with the panelists, and we already have the questions flying internally. So the topic this afternoon is bandwidth scaling for AI interconnect, more wavelengths versus more fiber. And if you'd go to the next slide, please, Dan, let's get right into this. And thank you so much, Tony, for setting up our panel this afternoon. You covered this very nicely. This is another very simplified view of the network architectures that are going on in a hyperscale data center that's running AI compute workloads. And here I've drawn at the top a front-end network that's typically a CLO network. Today, those are all cabled with optical fiber, single mode fiber typically, and they connect spine switches, fabric switches into top of rack. That's more of an established use case for fiber optics, but what's growing, as Tony alluded to, is this back-end network, and they're shown in blue are there are many networks inside the rack, but connecting together the GPUs or accelerators, XPUs, is a growing use case. And here's an example of what I'm talking about. This is an example from NVIDIA. This is their latest Blackwell chip and the DGX system that goes into. And in this one rack, they have 72 GPUs. And then connecting all of those GPUs takes this waterfall of copper cables to connect the backplane. There are over 5,000 copper cables, and I think you get a sense for the volume, for maybe the weight of those connections. And I think you can see that this might be a very good application for optics, especially as the number of GPUs grows beyond what you can put inside a rack. So next slide, please. I'm making Dan do the hard work. Thank you. So here's some research from Del Oro. And on the left-hand side here, the front-end network, and the right-hand side is back-end networks. And what Del Oro is reporting on here, they count the number of port shipments. Now, this isn't just optics. This is everything. This is the port shipments in a network. And so in a front-end network, you can see this very steady growth in the number of port shipments. That's important. That's just the number. But then the data rate that is also transitioning. And you can see there by 2025, 800 gigabits per second is the dominant port speed. In back-end networks, it's interesting. There's a couple of different trends. First of all, the number of ports being shipped is increasing much more rapidly. That's important. And then the pace at which we're moving through these different speeds is also accelerating. And so while maybe in 2025, 800 gig is also dominant, we move through 800 gig to 1.6T very quickly. And so these applications are diverging. Next slide. And this is an example of some of the performance metrics. I'm sure we're going to hear more about this with the panelists' discussions today, but just to frame things loosely, Interconnect today is 800 gig, but that's diverging. Reach, the front end is the whole data center, and the back end is rack scale. Power efficiency is very important. As you heard from Tony's talk, 20 picojoules per bit would be the power efficiency required for an optical module in the front end, much lower in the back end. And the cost targets are more aggressive in the back end as well. This is currently a copper solution, so much cheaper expectation. And next slide, please. So you saw that the transition, data rate transition is accelerating. So how do we do this in practice? In optics, we have a number of axes we can push on. To begin with, you push on symbol rate. But at 112 gigabaud, we're really pushing what's possible. And already in front-end networks, we are using PAM4. So we're packing more bits per symbol. PAM4 allows you to have 2 bits per symbol. And we could push on that some more with more complex modulation schemes, but it does come at the expense of power and complexity. So let's look at the number of fibers and the number of wavelengths. We have another 2 axes. And already in the front-end networks, parallel single mode fiber is an example of a solution that has 4 fibers in each direction. And CWDM4 is an example of having 4 wavelengths in each direction. So this has already been done, and the question to the panel is, what's next? Because we've got to keep going. We've got to keep doubling. And so what's the right parameter here to keep pushing on? So we have a fantastic panel. Next slide, please. And these are world experts in their fields, and I'm very happy that they accepted the invitation to come and talk about their particular view of what the right way to solve this problem is. I'd like to ask Dan Kuchta to come forward and join us front of stage. Hi, Dan.
Hi, Katharine.
And so Dan is at IBM, at the Watson Research Center. He's been there for very many decades and has done some fantastic work in a number of different areas of photonics. So please, Dan, share with us your perspective on this interesting challenge.
So many decades. Next slide, please. Thank you for inviting me to speak, Katharine and Dan. So I'm going to talk mostly about fiber and a little bit of less about wavelength, but I'll give you my thoughts on wavelength. I'm going to go and talk about some past examples of various projects that tried to use a lot more fiber. And I'm talking about single core ribbon fiber and multi-core ribbons. But I'll show you that the market has not been kind to high fiber count. In fact, it appears to favor fewer fibers and higher speeds. Next slide. So the past is sort of speckled with lots of high fiber count transceivers, and mostly multi-mode transceivers. So these would be the type that you would want to use in a back-end network. We had Zan Optics producing a 72 fiber module, Aerolite 36 fiber, TerraLink 48. None of those really got market traction. The one that did get market traction was the Snap 12, and maybe because it had an MSA, but that came out of Hewlett-Packard following their Polo and Pony projects, and it had only 12 fibers. So in general, high fiber count optical links, that's fine. You can leave it on that next page. Go ahead, next page. This is an example, a more recent example. This one had 336 fibers, and I don't believe they're in business anymore. But in general, the market has not been good or not been kind to high fiber count transceivers. Next page, please. So even within IBM, we pursued several projects with high channel count as a way to crank up the data rate. So here's our Terabus example. Terabus had 48 channels, so 24 transmit, 24 receive. What made Terabus unique was we coupled two polymer optical waveguides on a printed circuit board. The one thing I'll say about polymer optical waveguides is you can make them cheap. You can fabricate lots of them lithographically, but adding them to a printed circuit board invites a whole host of other issues that make them difficult to implement. Next slide, please. So after polymer waveguides, we went back to high fiber count. So we just did a 48 channel device with a 4x12 fiber array with a tight band radius. Next slide. And then trying to get away from high fiber count, we went to multi-core devices. So essentially we took the same 48 channel device, but we replaced it with eight 6-channel multi-core fiber. And so, we looked into, could you have arrays like MTP connectors with populated with multi-core fiber? We studied that for a while, and it's possible to build those. It's possible to put all your optoelectronics, to sort of match a multi-core fiber array in a butt-coupled manner. It becomes really tricky to wire up the circuitry to the same level. And then in the end, we didn't see a cost advantage. Multi-core fiber invites its own issues. Next slide, please. Here's another example. It wasn't just 6-core hexagonal. We looked at 4-core square as well. Next slide, please. And I want to say something about yield. In the Motion project, we had done a 16-channel transceiver, but if you look at the picture of all the dye on the glass substrate, you'll notice, certainly in the photodiode, that there's sort of 4 different shades of gray there. And what that really is we found that while in principle you can make arrays of 16 devices, what we found in practice was that 4 arrays of 4 channels yielded better than one large array, and that's including assembly and test. And that's sort of where I'm thinking that some of this needs to go is, numerous small transceivers with lower channel count. Next slide, please. When we go to high channel count, we need to consider reliability. And for the Motion project, which had 16 channels, our approach to reliability was to use 2-to-1 sparing. And the way we did, so first thing, just theoretically, 2-to-1 sparing will buy you about 3 orders of magnitude improvement in reliability. It's pretty powerful. The way we implemented it was our 1x4 array of VCSELs was really a 2x4, where alternating rows had orthogonal polarization. And then I'm just showing a little sort of ray tracing diagram, how we coupled the 2 polarizations into one fiber. So it doesn't really matter what you do or what technology you have. Sparing, I think, especially for high channel count, I think sparing is something that has to be included. Next chart, please. And then for high fiber count connectors, so in the market today, you can get a 72 fiber MTP from US Connect. Furukawa, at one point, almost 10 years ago, made a 96 fiber connector. That's not commercially available. Both of these fibers are multi-mode. Both of these connectors are multi-mode, though. What I'm seeing in single mode, what's available today is up to 32 fiber, 2 rows of 16. I'm told that a 48 fiber is on the horizon, so 2 rows of 24 where they drop the pitch to 165. But over on the right is kind of a complicated chart, but the message of the chart is that the more fibers you put in a connector, the higher the cost is. In fact, a 72 fiber MTP72 cable is about 8 times the cost of 6 12 fiber cables. So same fiber count. It's just a lot more expensive. And the same holds true for the single mode case. An MTP32 is about 3 times the cost of 2 MTP16s. And part of this is that the piece parts themselves are more expensive. It's more labor intensive to assemble these high fiber count connectors, and the yield is lower. And the other thing that I find going on in our industry, we have a lot of work to automate transceiver assembly and test, but our fiber connectors and cables still involve a substantial amount of manual labor. And so I think that's sort of goes against moving to high count fiber connectors. Next page, please. So a couple of comments on wavelengths. I feel that a small number of additional wavelengths, like 2 or 4, is relatively easy to add without much additional cost. Of course, wavelength spacing avoids temperature control. A large wavelength count implies a small wavelength spacing, and so that then requires some degree of temperature control or wavelength control, which is going to cost some amount of energy. And I've tried to make the point that reliability drives some sparing requirements. I don't have a chart to show this, but wavelengths are harder to spare than fibers or other things that share a fiber. I'm sort of putting out a question, but how do you spare a comb laser? Because when a comb laser goes down, it's not like it takes out one wavelength. It takes out all of its wavelengths. And that seems to be a single point of failure for many channels. So that's a concern for adding a lot more wavelengths. Next slide, please. So just some additional comments. There are some advantages to adding more fiber. You can have lower crosstalk, and that would be lower crosstalk compared to, say, WDM. I don't have a slide for this, but IBM spent a lot of time looking at parallel buses with a forwarded clock, meaning that we're devoting an extra fiber to sending a forwarded clock. It does lead to some tighter skew and jitter requirements, but it leads to lower energy and lower latency and lower BER. I did mention that polymer waveguides can be made cheap, so you can add a lot of them, but they invite a whole host of other issues. And then the disadvantages of more fibers is the fiber bulk. Maybe multi-core fiber can offer some relief there. But I tried to drive home the point that there's a big yield disadvantage. It's really hard to yield a large number of optical devices, and it's harder to yield high count fiber connectors. The reliability does scale to the power of n, and you definitely need a sparing and redundancy scheme. Okay, I think this is the last slide. Next one. No, one more slide. Okay. Katharine wanted us to talk about energy. My quick remark about energy is optical links are essentially analog in nature. And so when we look at analog CMOS, they have this property that I'm showing in the upper right, which is there's a certain minimum energy just to turn on the circuits. And below that minimum energy, the energy per bit goes up. And then above that minimum energy, the energy per bit also goes up because you're hitting the... So on the left side, it's going up because you have fewer bits that you're amortizing the energy over. And on the right side, it's going up because you have to push more current in to overcome the bandwidth limits. So each technology node has a different optimum data rate that minimizes energy consumption. So there's no like one correct answer. It really depends on the technology node that you choose. And also going slower generally does not improve the energy per bit once you're below the data rate of the minimum. Okay, next slide. This is the last one. So in summary, I didn't have a slide that says this, but optics cost is what really dominates everything, dominates all the decisions. Cost appears to be minimized when you are running your optics at the highest data rate that they can support. I don't have a strong opinion on more fibers versus more wavelengths because adding either adds cost, although I really think until they start automating fiber connector assemblies and improving on the yields, adding more fibers, I think, is more challenging than adding more wavelengths. I do think that this suggests a large collection of medium lane count transceivers might be optimum, especially if they have very small packages and can be packaged right next to each other. And then, of course, the real optimum is going to depend on the exact application and the technology node that you choose. Okay.
Well, thank you very much, Dan. That was very interesting, and I'm looking to see, I actually don't see any questions. And since you did share quite a lot of information, which I think is wonderful, thank you for talking about cost and energy and sharing your experience over many different types of technologies. That's great. So
I saw one question from Jeff, but I don't know how to answer it. I don't know the answer to your question, Jeff. Katharine,
okay.
do these questions come through?
I don't see Jeff's question.
Are you seeing it on the Slack channel or are you seeing it in the chat, which is not?
I'm seeing it in the question and answer on Zoom.
Yeah, really?
Anyway, so Jeff Hutchinson's question is, do you see a roadmap to automating fiber connectors in the industry? And that's a good question. I'm not the right person to answer that question, but I feel that I feel that the amount of manual labor in cabling and connectorization is something that really needs addressing, as much as automating transceiver assembly does.
There's another question before that. How do these types of limitations map to new optical transceiver technologies such as micro LEDs? I think that'll be addressed by some future panelist.
I'll let Bardia answer that.
And I do see one other question has just come through the Slack channel. And since you mentioned it a few times, let's clarify. What do you mean by medium count transceiver?
So medium count, if I look at where single mode seems to be, they're getting the 16 channel connector done about right. Similarly for multi-mode, although weirdly the 1x16 ends up being a little bit more costly than the 2x24. I'm not sure why that is. So I think in that range, maybe the sub 32 channel range, 16 to 32, is where I would think of as being medium.
Great. Thank you very much, Dan. We'll have Dan come back for the panel Q&A later on, and I'd like to call Peter Winzer. Would you join us front of stage? So Peter has had a long career at Bell Labs, and has focused on SDM, spatial division multiplexing, more recently, of course, in his work with submarine. You know all about multiple wavelengths. And here he is with Nubis, focusing on datacom. So let's tell us about how you see the right solution, Peter.
Thanks a lot, Katharine. Thanks for your introduction and for inviting me to this panel. So I'll talk about high speeds over lots of parallel fiber, and I think that's the best for optical datacom I/O, as you shall see. So next slide then, please. So first of all, we all need to remember that every communication is high speed because any processor I/O operates at a multiplex of the clock frequency. The clock frequencies are 1 to 2 gigahertz for processors, and everything that we do in electrical and optical operates at many gigabits per second. What you see here in this table is a summary of 3 prevalent electrical interfaces, HBM3, UCIe, and SerDes, that go from all the way 6 gigabits per second to 200 gigabits per second for modern SerDes. And which speed you choose depends on a couple of different trade-offs. Some of them are related to the processor itself, in terms of how much area in the chip do you want to spend for your I/O macros, and also the breakout of the processor. What's your bump density, what's your packaging strategy, and your packaging complexity. So that's one part that determines the solution you're going to choose. And another one is the transmission medium itself, like what lane densities are we talking about? Are we talking substrates, PCBs, maybe even twin-ax cables? What distance do I want to achieve, and what complexity am I willing to afford on my transmission medium? So all of these represent a trade-off space that we need to consider when we talk about interface technologies and speed. But one thing is for sure, if you want to go beyond the centimeter case, that is best supported by high-speed SerDes. That has been true and is true today. Next slide, please. And the good thing is that optics likes fast. So optical channels support high speeds because they don't have this roll-off that you see on electrical channels. Optics is by nature broadband. And the good news is, and Tony alluded to that in his keynote as well, that modern SerDes can directly drive optics, especially if those optics are built to look linear, to look like an electrical trace to the SerDes. Then the SerDes can directly drive the optics. You don't need any signal reconditioning or retiming in your optical module, whatever that module might be. You can also use converter chiplets. That's again, as Tony said in his keynote, like a UCIe to SerDes converter. If you want to take advantage of the chiplet ecosystem and you want to have your processor speak UCIe to a converter chiplet that then converts that to high speed, and then same story applies, you go high speed over optics. And these two solutions, by the way, consume the same power. End to end, it's a wash. Next slide, please. Okay, now let's talk about slow optics versus fast optics a little bit. So the advantage of fast optics is that you can directly drive it with SerDes. The disadvantage of slow optics is that slow processor IOs cannot directly drive slow optics, typically. Typically, what you do is you use some sort of digital signal conditioning, retiming, or gearboxing as part of your optical engine that needs to reestablish the signal quality, because these die-to-die interfaces are not meant to drive optics at the low speeds. Also, slow optics need much more components. You need more modulators, more photodetectors, which becomes a size and a yield issue, as Dan also said before. And also, slow optics poorly amortize per lane overheads. An example for that is modulator bias, for example, which is a fixed cost essentially that you have for a channel. If it's a slow channel or a fast channel, it doesn't matter. You need that bias. And another one is fiber density. You can't afford to send 25 gigabits over individual fibers because the density wouldn't allow it. So you need multiplexing like WDM if you speak about slow optics. Next one, please. Okay, so here is an example just to show, to dismiss the myth a little bit that slow is better energy efficient than fast. These are actually hardware demonstrated things. This is not PowerPoint engineering. This comes from people reporting actual end-to-end experiments at 16 gigabit with eight wavelengths and 100 gigabit with one wavelength, both silicon photonics up to a couple kilometers reach, and both consume about 10 picojoules per bit end to end, if you count everything in, including the SerDes in the host processor. Interestingly, the slow solution that was again actually demonstrated shows about 300 gigabits per second per millimeter, whereas the fast option is N by 500 gigabits per second per millimeter. And what do I mean by N by 500? That's shown on the next slide. The fast option, if you leverage SerDes, what it allows you to do is you reach it further back away from the chip. You can reach multiple rows of optical engines because your SerDes can drive it. There is no problem bridging those longer distances with your SerDes. So if one row has 500 gigabits, 2 rows has 1 terabit per millimeter, 4 rows has 2 terabit per millimeter. So you can stack up if you do things correctly, and if you leverage this SerDes and the 2D tiling architecture, which also means you need to escape in the third dimension, just as Dan showed with the multimode. So escaping in the third dimension with a 2D array is definitely a good thing. Next one, please. Okay, so now we're all convinced that high speed is the right way to go. So now the question is, should we send high speeds over dedicated optical fibers, like continue the electrical trace all the way through the optical fiber without any change, or should we use multiplexing by either WDM, polarization multiplexing, coherent, or even bidirectional transmission? So to answer that, we all need to acknowledge that multiplexing is a means to amortize expensive channels. That's true in all of engineering. You only multiplex if the channel is so expensive that you need to share it among different participants of the communication paradigm. And if you go to the next slide, then we'll ask, how expensive is a fiber? So this channel summarizes, this table summarizes the cost of a fiber all across optical applications, all the way from submarine trans-Pacific cables to MLAI clusters. And the cost here is given in multiples of a 200G transceiver cost. So a trans-Pacific fiber, one extra strand of fiber costs 600 times the cost of a 200G transceiver. And that, of course, means in submarine, you need to multiplex as much as you can to amortize the cost of that fiber. So you use coherent, QAM, Polmax, WDM. You throw all multiplexing possibilities at that problem to amortize that cost. But for short distances, 10 to 100 meters, the cost of an additional fiber is in the single-digit percents of a 200G transceiver. So there is no need for multiplexing from a cost point of view. So you use parallel fibers. That's a good thing to do. Okay, next one. So here is an example that shows how multiplexing also costs you power. So what I compare here is an 8 by 200G DR8, so one wavelength over 8 fiber pairs, versus an 8 by 200G FR8, so 8 wavelengths over 1 fiber pair. And the E2O and O2E has the same power consumption because you use the same amount of modulators, the same modulators really, but the lasers are pretty different because for WDM, you need to go through a mux-dmux pair, which if a mux and dmux has 1.5 dB loss each, that's 3 dB. So you double your laser power. And also the efficiency of the lasers tend to be much better if it's just a single wavelength unstabilized laser. It's much better. I here only assume 20% to 15%. It might be, the difference might be even larger than that. So that just shows you that multiplexing comes at a cost. And that's what we need to acknowledge. Okay, next one, please. So then there is another aspect to the issue, and that's networking. So usually you want to do full radix switching. You want to break out all your links to multiple end nodes or switches to build those clone networks that Katharine talked about in the introduction. And in order to do that, you need a network-capable protocol. So you need to use like Ethernet, InfiniBand, NVLink, something like that, where you can actually do networking. You can't just use any proprietary interface or die-to-die interface that's not meant for networking. So that's very important, and that favors single wavelengths. And next one, please. So if you multiplex those up into WDM, then you have these big fat pipes, and you can't do networking with those big fat pipes. Then it's an end-to-end big fat connection that's not suited for any networking application. Next one, please. So this is just the conclusion, what Nubis, how Nubis solves this problem with the XT1600 ultra-high density optical I/O. You see on the left side, our near package optics module with 16 by 100 gig full duplex has a 15 by 15 millimeter footprint. And if you gang that together in a staggered array, because we can, in terms of the 2D arraying, we get 10 terabit full duplex on the footprint of half a business card. That's sort of what we can do today. You see in the table all the parameters that matter: high I/O density, low latency, low power, full intra-rack to inter-row connectivity from 1 meter to hundreds of meters, full radix networking because we use single wavelength, multiple fibers, and full network compatibility with all the networking protocols that are out there. Thanks.
Thank you very much, Peter. And I'm looking to see if there are any questions in any of the different forums. I don't see any. Oh, Dan, do you have a question? Did you see one?
Yeah, no, I didn't see one. I just have one. Very
Good.
quickly, Peter, here. What is driving these fibers? Is it lasers or LEDs?
Oh, this is laser-based. This is silicon photonics. You have lasers that are modulated by silicon photonics modulators.
Okay, thank you.
And I have some questions regarding the size. Could you you did mention it, but it was kind of fast. What the PCIe card that you show there? What is the chip on the right-hand side that you're showing that up against, and what's the scale that we're talking here?
Oh, so this is just a mock-up. This PCIe card is a mock-up. It's a regular size PCIe card. The modules themselves, I don't know exactly how big the chip is or the modules, but one of our modules is 15 by 15
millimeters.
Millimeters, yeah. Mm-hmm.
Thank you. Again, I don't see any more questions, and we are a little behind, so let's move on, please. Thank you very much, Peter.
Thank you.
And I would like to call Rebecca to come forward. Yep, that was fast. Thank you, Rebecca.
You're welcome.
Rebecca Schaevitz is at MixxTech Technology. She has a long career. You may have seen her. She's certainly got a lot of experience in the industry, working at Corning and at Broadcom. So she knows what she's talking about. And please share with us what you think the right solution is, Rebecca.
Happy to. Thank you, Katharine, for the warm introduction. As Katharine said, I am at MixxTech Technologies. I'm the co-founder and chief product officer, where we are scaling AI sustainably. I also love that the keynote and talks before, we talked a lot about how to scale, but also how to do it sustainably in a way that's power efficient. Next slide. So before we get into answering the question at hand, I do want to restate the problem that we're trying to solve. That's always first and foremost the important aspect of what we're doing here. There's a lot that we've done in history in the optics field, but as the market shifts towards these AI models, we also have to shift a mindset. So when we look at AI specifically, some of the things that are called out that Katharine spoke about, keynote speaker spoke about, is these very, very large models, many, many GPUs or XPUs generically that are connected together. And that requires inherently a lot of interconnects. And if we use today's technology, that means we have a lot of overhead on networking because we want these to be full bandwidth, non-blocking scenarios. And that means a lot more switches, a lot more interconnects in order to adjust to that. In addition, when we add on these networking layers, we also add on things like latency and variation to latency. And those are compounding our needs for memory access because we need to store more data while we wait for all the data to get through the network itself. And that memory also needs interconnects. So now we've compounded this problem of interconnects, not just in meeting the GPU requirements of talking to each other, but also in accessing memory. And all of this overhead means that we are exploding our cost basis, right? For each GPU, we have a lot more components that need to work reliably, which means we buy even more to have redundancy, and we're exploding these costs. And we have a huge imbalance of resources going on. and decreasing cloud margins, right, as we do these, inquiries into the models. And that all burns a ton of power. So how do we solve this problem, right? We do need to fundamentally solve the massive load of interconnects, and we need to do this in a hardware solution. Next slide. Not only that, we also have this huge diversity in what's needed, right? Meta presented last year at OCP a really great diagram of showing how, whether you're doing training or you're doing inference, you might need very different solutions. And then not only that, you might be doing a large language model, or you might be doing recommendation ranking, and there might be future things like video processing and things that we haven't yet discovered today as being necessary. And these are varying things like model size or scale, your memory needs, your network latency. And one of the things I want to point out is on this plot, every single one of those parameters are influenced by your interconnect capabilities other than compute itself. So if you need more memory, you need to interconnect to more memory, right? A network is, I think, very clear. But if you need more models, we need model sizes and more nodes, we need to interconnect those. So these are all incredibly important aspects of how we scale AI. Next slide. So as speakers have mentioned, optics is needed, right? You're getting to longer distances beyond what a copper can reach. So we know optics is absolutely needed, and it's growing substantially because of AI. Next slide. I think Marvell had a brilliant graph just showing the level of imbalance in the network when it comes to optical connectivity, right? If you take 128 XPUs as a cluster, we're at a 1-to-1 overhead. When we get to 1 million, we're at a 10-to-1 overhead. It's a huge discrepancy in terms of what we need to design toward and the volume that we need to design toward, which is very different than history has dictated optics to drive. Next slide. So we kind of saw this coming. We said, oh, we're going to need some solution here. And we have tried to migrate from standard optical pluggables into things like onboard optics or a substrate-based CPO integration. And I call that substrate-based. It's a kind of a 2D integration where we are limited by the substrate density in interconnects versus the PCB density that we're limited by in an optical pluggable case. These solutions that we've been working toward have provided things like better bandwidth, better density, better radix, but they have not yet been adopted into volume. And the question is, if AI needs all of this, why hasn't it yet been adopted? Next slide. And the answer, and I love that in the keynote this was alluded to, packaging is a really big challenge, right? Dan even mentioned this, packaging is hard, and it historically has been hard. And the more you add fibers into the mix, the harder it is. And part of it has been our mentality of how do we scale up a transceiver rather than how do we integrate with ASIC technology as it's manufactured today. And that's where we need to have a paradigm shift in how we actually approach optics in this new world. Next slide. And so that's what I call the siliconization of optics, where we are designing optics in a way that's directly compatible with existing advanced manufacturing processes without disruption, where we have automated processes that doesn't need a technician to come in and intercept or active alignment in order to create that solution, where we're focused on how testing happens throughout that process, how manufacturing happens throughout that process, and center the design on those requirements, where we stay pitch matched to the fundamental die itself that we want to get that interconnect off so we can scale with the ASIC die. And we can do all of this at wafer scale. And that is what's critical in the optics field and creating those solutions that enable the whole industry to shift into the volumes that are needed for AI. Next slide. So you're going to have to step through this with me, Dan. If we talk about copper, next. that, is kind of the fundamental basis, right? It has the lowest radix, lowest reach. The number of XPUs you can get in a cluster for a given latency is relatively low. It's something like 8, right, that you can fit on a board. Next slide. Now, if we add optical transceivers into that, we can increase that reach, which is great, but we're not increasing the density because we're still limited by the PCB and the I/O through cages, right? So we haven't really solved the problem. Next slide. So we can now go to 2D type integration on a standard CPO solution, and we can improve radix because we can now have the density of a substrate in terms of the interconnect capacity to your optical engine. So you get some improvement in there, and then you can get more XPUs in a cluster for a given latency. That's great. What we're driving at Mix next is to really dramatically change that. And here's the answer to your question, Katharine. I believe that scaling radix is the fundamental that you need to really drive solutions for AI and what they need. So with an enhanced radix and the innovative design to make sure that you stay within the advanced manufacturing pipeline, you can get something like 800 XPUs in a cluster that's less than 50 nanosecond latency. That's the equivalent of what we do today on a board with 8, right? So that's 100x improvement. We can get things like 500x, nearly 500x improvement in these large model for training, which gets us to that 1 million or further mark, or provides redundancy, things that have, challenged the reliability of those networks. And with that, you're also creating a solution that can integrate whether it's in the back end or the front end of the network, because you're DR compliant and you can match any of the lower density systems that are already out there that maybe you just want to throw a transceiver into a single box sort of solutions. And so in that way, you're solving the problem that is actually important for the AI industry. Yes, it makes it challenging. Yes, you have to solve the packaging, but that's what we need to drive to as an industry to make this real. Thank you.
That's very interesting. I have one clarifying question for you. When you say increasing radix, are you excluding putting more wavelengths to increase bandwidth, but then you have the opportunity to have different fibers, take you to a different endpoint, so meet that radix, or?
Yeah, so radix very specifically to me is based on what you're carrying over the fiber, right? And I am not against in the future scaling with, let's say, FR technology, where we could add more wavelengths to increase the bandwidth that you have on a given fiber. But you have to first solve the fundamental and make sure you have a design space you can work in that has sufficient radix for what's needed in the industry.
Sounds good. Thank you very much, Rebecca. And in the interest of time, I would like to call our next speaker. Amit, would you step forwards? And Amit Nagra is at Intel and recently joined. He has a long history in photonics from Source Photonics and Rockley Photonics, and he's currently the VP and General Manager of Intel Silicon Photonics Group. Please go ahead. Thank you, Amit. Tell us about your solution. If you could unmute for us, please, Amit. Thank you.
Thanks for the opportunity, Katharine and Dan. If you go to my first content slide, let's flip through all the way. And if it has some kind of automation. There we go. Yeah. So next, please. I think through this presentation, keeping the key question at hand, which is, how do we scale for AI networks? Is wavelength more important? Is fiber count more important? I think this is a mix or a synergy of our experience at Intel, along with many of the panelists before. Having shipped silicon photonics modules into this industry since 2015, we've seen the need for both DR and FR, and at every speed node. And so that was our history when we were a pluggable transceiver purveyor out of Intel. We're no longer doing that, but we are partnering with pluggable module vendors, and we're providing the key chipsets that go into it. And we continue to see the need for both DR and FR, and at every speed node. So as Katharine mentioned, this is the front end of the network mainly, but some of these are also making their way into some backend applications from what we can tell from our customers and our customers' customers. So the transceiver space has clearly shown a need for both. What we have done when it comes to optical I/O connectivity at Intel, which we call some of our OCI projects, and we did a recent demonstration of this at our Foundry Day, is a 2 terabit per second package, 4 terabit per second total bandwidth bidirectional, and it used 8 fibers and 8 wavelengths per fiber. So we were using both levers to cram in that density. And in our case, that wavelength matrix is actually a closely spaced grid, closely spaced wavelengths on a floating grid with the associated control technology. So we believe that that lever allows you to get up the density as well as the cost per bit and the power per bit, in line with some of those targets that Katharine had shared earlier. Although Katharine, in your slide, you mentioned 50 cents a bit, and I'd love to sign up for that kind of pricing model. But kidding aside, on the next slide, when we talk about what the application needs, you know, the power and cost is front of mind. And I think you've seen some of these numbers before in the slides from the panelists. But one thing that Katharine requested me to focus on, and this is something that Dan opened with, is also the reliability expectations of this. As you're attached to more and more precious endpoints, and you have more bandwidth flowing through your particular component, the reliability expectations go up. And as those reliability expectations go up, many of the solutions you see have a very high component count. And what that means is the reliability expectation for a given component goes up even higher than that. So you know, we've addressed that through some very innovative ways at Intel, in addition to many of the other vectors. And in my talk, I'll talk about that a little bit more. So if we go to that next slide, one of the things we wanted to indicate here is, and this is why when we look at AI applications, we think of it as an and, or more like a sequence of which levers to pull when, as opposed to, do I pull just one lever and which one is it? And it's because if you look at the interaction of these, as you go up in wavelength count, we do see it being beneficial to power reduction. We do see it being beneficial to cost, but it does have an impact on shoreline density and overall density of the solution. Line rate, you know, it at least up to these rates seems to be good across the board. And so for those reasons, you know, we are supporting the highest line rate that our technology can support. And, you know, so far, at least within OCI, we've been able to keep up. Fiber count is, in our experience, been a weaker modulator of these parameters. The polarization knob is available. I think Peter talked about it earlier. So this is something that is available in reserve for, you know, pulling that lever when the total bandwidth will actually need it. Higher order signaling going to potentially coherent, again, comes with a huge complexity and cost penalty. But in the front end network, as Katharine mentioned, you know, we've already pulled that lever, right? We've gone from NRZ to PAM4. And even in some of our conversations on OCI and CPO, in some cases, the sheer density needed in some of these applications require you to pull that lever. So, our take on it is these are all knobs that are available, different applications. You know, Rebecca talked about radix. You know, by definition, if you want to go many places, the easiest way to do it is with many fibers, as opposed to first combining it into a single fiber, then splitting it out, which has huge penalties. So it's very application dependent. Within our platform, we support multi-fiber attach in an automated way, like Rebecca mentioned. We have both coarse WDM as well as finely spaced O-band wavelength capability on the same chip. So what we are trying to do is make sure that the platform is ready and has these levers available to invoke in a cost-effective and reliable manner when the applications demand it. Next, please. And so this is talking a little bit about, what most people perceive as probably the single weakest link in an optical link from a reliability perspective. I have a slightly different point of view, but I want to address the laser anyway, since everybody talks about it. I think fiber attach is the weakest link, but probably firmware quality is even higher than that. But fiber attach from a physical part perspective is probably the weakest link, and goes back to many of the things that Dan talked about, how our fibers made, how they connected, the manual nature of processes, the materials, the mismatches. But focusing in on lasers are very well understood, and some of the mechanisms that lead lasers to fail are also very well understood. And when we put together this silicon photonics platform with the integrated laser, which has the 3-5 material co-processed with our 300 millimeter silicon wafers, we leverage that opportunity to actually solve many of the issues that cause laser failure by design. So for example, facets are a failure point. We don't have facets in our architecture. We have evanescent coupling of light in and out of the gain material. So you eliminate a failure mode by category. The regrowth interfaces have been eliminated. We put the gratings in the silicon as opposed to the 3-5 material. So many of these things where we've seen, where lasers have traditionally failed, we've addressed them by design. Then that still leaves another category, which is material quality and random defects. Typically in photonics, we don't care too much about random defects. In photonics, typically the focus is on parametric yield. Are our devices good enough that you can cascade them together to meet your functional specs? And I think we're getting to a point, whereas the digital CMOS world is very different. Parametric yields are insanely high, and people focus on defect density. And as a result of that, 300 millimeter manufacturing lines, especially digital CMOS lines, are very well suited to track, identify defects, and then find out what is their root cause and eliminate them through process control. And these are methodologies that we've embraced. And while for the rest of the photonic circuit, it doesn't matter too much because it's very sparse, this has led to a lot of improvement on the laser side. As a result of that, our field experience, as well as our internal reliability programs, where we run a huge number of volumes through stress testing, our experience has been laser fit rates of less than 0.1 per device. And for the rest of the industry, low single digits is an aspirational goal. We didn't luck into it. It was partly by design and a lot of hard-fought battles. It hasn't mattered much in the transceiver space because you don't have the device count. And like I mentioned, there's other things that fail at a much higher rate than the lasers do. But for this next frontier, we're ready and excited. Next slide, please. The quick recap. We don't believe one approach, all multi-fiber or multi-lambda fits all applications. You will need multiple levers. We plan to continue to support within the front-end network pluggable components, both the DR and FR formats. And when it comes to the connectivity market, the XPU connectivity market, our solution relies on both. It relies on both today, and we plan to keep relying on both as we go forward. Thank you.
Thank you very much, Amit. That was very thorough, and thank you for digging into the topic of reliability. It's a very important one. Now, I don't see any questions, and I don't have any clarifying questions. Dan, did you have anything top of mind? If not, I think in the interest... Oh.
I was muted. Just on this slide, see, I have access to the slides. And in the bottom right, you're showing an indium phosphide die on a silicon wafer. How do you do that integration?
Yeah, so it's very interesting. There's many ways of hybrid integration, and often what people will do is find a way to process your silicon wafer, process the indium phosphide die, couponize or segregate the indium phosphide, and then align or integrate. The way we do it is we do the front section of the device. We do waveguides and all kinds of things, gratings early on a 300 millimeter wafer. And then we have an optimized epi that we do in-house, which is designed for our integration. We take those 3-5 coupons, we take those 3-inch wafers of indium phosphide, we couponize them, and we flip chip bond them en masse onto a huge wafer, 300 millimeter wafer. And then we co-process them. So it's not a laser, it's an epi stack before. You put it on and you co-process the laser at 300 millimeter scale. So it's physically aligned. That's how we can get light in and out through evanescent coupling. But so it's not an active alignment of a laser after the fact.
Great. Thank you so much.
Very, very clever. Thank you. Thank you very much, Amit. I would like to call our next speaker forward, Alan Liu. Alan Liu is CEO and co-founder of Quintessent. And you may have seen him. He's been active in the industry for some time. If you've worked on a DARPA program, you have probably seen Alan there. So please go ahead, Alan, tell us about Quintessent and your solution.
Sure, it looks like Dan is still pulling up the slides up. Here we go. Well, first of all, thanks, Dan and Katharine, for the invitation. It's an honor to kind of be here with the rest of the esteemed panelists and looking forward to the discussion, and I'm learning a lot. So at Quintessent, we've been working on high wavelength counts, specifically DWDM technologies for DWDM-based interconnect architectures. And so with respect to the panel discussion topic, I have a very clear opinion, which is that life is better in color. And for the avoidance of doubts and ambiguity, by color, I mean wavelengths. So next slide, please, Dan. And I'll share my perspective from the, I'll kind of examine the question from the lens of, both performance and operational considerations. And obviously a nuanced topic, but in the interest of time, I'm going to try to distill, it down to sort of what I perceive as the key considerations. So first of all, why not more fiber? Obviously, AI clusters today use a lot of breakout applications for increasing radix, DR4, DR8, sort of the predominant workhorse for the backend GPU to GPU connection. But in terms of looking at the scaling out in the future, one important metric is that not only is it important to have radix, but bandwidth per fiber or bandwidth per effective radix ports also needs to grow. And so that by definition eliminates scaling just with adding more fibers alone in parallel, or takes that option off the table in terms of trying to meet this requirement of accommodating bandwidth per fiber growth. Next, please. The other consideration is that reliability at a system scale, at the data center scale, and many of the panelists before me have touched on this before. There's obviously lots of different considerations here in terms of what determines the overall system level reliability, starting from the material level to the component to the link and then all the way to the application level. But we kind of look at the key relevant ingredients in the context of the discussion. Every mechanical moving part in the data center or in the cluster is a potential point of failure. Every fiber termination has potential to have dust in it. Every additional strand of fiber has potential to break, et cetera, et cetera. And also, every additional parallel fiber adds complexity and cost in terms of alignment, and also presents some yield issues there. So trading off fiber terminations where you can for things that can be brought onto the chip on the wafer is the path to improving overall system level reliability, because that eliminates, it moves the failure points from things that are mechanical and moving to things that are stable and on the wafer. Next slide, please, or next click, Dan. And then finally, I'll make the notes that cabling in state-of-the-art large-scale GPU clusters, like the one that was just recently brought up by Tesla and X.AI, is already a nightmare. So this photo is, showing the sea of yellow SMF fibers that are prevalent and also just bundled on the floor. And overall, that looks like a messy nightmare. And if we're asking whether we want to add to that mess, pretty scary proposition to me. So in addition to this, I think another consideration is that obviously for greenfield deployments of GPU clusters, you have the flexibility to lay down, brand new fiber plants and fiber architecture and installations. But I think in general, in the past and likely in the desire and as a desire for the future, it would be nice to put down a fiber architecture and fiber plant on day one and have that last across multiple GPU generations. And so from that perspective, it's nice to be able to reuse the existing fiber infrastructure when you're going through multiple upgrade cycles, and scaling in wavelengths by just adding more wavelengths per fiber and reusing the fiber infrastructure allows you to do that, whereas adding in more strands of fiber is a huge operational undertaking. So next slide, please, Dan. All right, so let's play the devil's advocate for why not more wavelengths. One thing that I think I see around the industry is that, in terms of the choice of one potential consideration is just, photonic elements, especially components on a chip, usually have a finite spectral bandwidth or wavelength response. And specifically in the context of the choice of fiber couplers, there's really only two choices: edge coupling and vertical coupling. And everyone has their religion between the two. Some people prefer vertical coupling for high throughput wafer level testing and manufacturing. And in those cases where that is a strong consideration, then you would be limited in your flexibility of, or in the total range of the wavelength spectra that you have to play with. For example, you want to be able to use a CWDM grid, and you want to be able to just add additional coarse wavelengths at will, for example. But one solution to get around that is to move to a denser grid. So instead of 20 nanometer CWDM, maybe consider 2 nanometer DWDM, for example. And that's what we're interested in exploring at Quintessent. Next click, please, Dan. The other traditional, arguments against wavelength scaling, which has been touched on in this panel already, is that wavelength scaling is expensive because traditionally, when the method of scaling bandwidth by adding wavelengths requires the addition of an additional laser, the incremental cost of that wavelength or extra bandwidth is the cost of another laser. And so you have a pretty steep incremental cost of bandwidth scaling curve that is more or less the cost of adding more lasers or for additional wavelengths per fiber. But one solution to get around this is, again, if you're using a DWDM grid, advanced, please, Dan, then you have the option to leverage, advances in comb lasers, specifically DWDM comb lasers, that gives you the functionality and wavelengths of multiple lasers, but for the price of one. And so that breaks this cost scaling curve where instead of the steep increasing cost as you add more wavelengths per fiber because you have to pay for an additional laser, that cost can be pretty flat because you're amortizing the cost of a single laser over multiple wavelengths. The third, argument against wavelengths, next click, thank you, Dan, is that wavelengths are difficult to control. And again, I would say that has been true traditionally when you're architecting and building interconnects that use single lasers per lambda. But again, there's solutions to this. So Dan, if you can advance, please. If you're already using the DWDM grid and you're using DWDM comb lasers to break the cost scaling curve, then you can also leverage the fact that, at least for the lasers that Quintessent makes, the wavelength spacing between wavelength frequencies in the comb laser is very consistent and very repeatable. And so if you know where one wavelength is, you know where the neighbors are, and all of those wavelengths track and drift together. And so that's a lever that allows you to then simplify the control of the wavelengths in the high wavelength account DWDM link that uses this technology. And we've shown that you can get very repeatable and very predictable spacings in comb lasers for the frequencies variations less than 2%. So next slide, please, Dan. So in the final analysis, another observation is that the two aren't necessarily mutually exclusive. You can scale up in fibers to achieve more radix. And on top of that, you can also then add more wavelengths to the same fiber. So both can be used to, depending on the application and need. And so, for example, whereas 800G DR8 is sort of the workhorse interconnects for backend networks today, before we think about adding more fibers, why not shove more wavelengths down each fiber? And so, potentially we can have 8 wavelengths per fiber, still in a DR8 configuration for the radix, but now we're talking 6.4 terabits total, or 800G per fiber, which is very interesting. So in general, I would say reliability, simplicity of deployment and upgrades, and also the need to drive up per fiber bandwidth growth necessitates wavelength scaling. Obviously, radix is very important too, which has been talked about in this panel, and that favors having more fibers for the breakouts. But that up to a limit, right? You only have a certain number of ports on your switch, and so if you have more breakouts than the port count, then you're talking about either adding more switches or more layers of the switch, which then becomes another cost driver. So in the final analysis, Dan, if you can click one more time, my assessment is that both are likely needed to scale up AI clusters, but obviously, in my opinion, life is always better with more color. All right, thanks very much.
Thank you very much, Alan. And I have a quick question for you again, clarifying. How many wavelengths are we talking? How many times can you double?
We see a pretty good path to having 32 wavelengths on per fiber, and that's what we're working on or towards. Initially, it'll be in groups of 8. And Peter talked about that it's not ideal to run each wavelength slow. And I'll just add that wavelength scaling and WDM and wide and parallel doesn't have to mean wide and slow and parallel. You can have lots of wavelengths and still run them at modest speeds, right? So in this DRA example, I'm imagining that each wavelength's at 100 gig per lambda.
Thank you. Well, thank you very much, Alan.
Thank you.
And I don't see any questions for Alan here on any of the channels. So I will go ahead and call our final speaker. Bardia, would you come to the stage? And I don't see Bardia coming yet. Somebody could help Bardia. So let me go ahead and introduce them. There's enough people backstage, I'm sure, who can help him come through. So Bardia is a co-founder and CEO of Avicena, and Bardia is a serial entrepreneur. So this is not his first rodeo. He's done many startups in the past. I would like to hear, Bardia, tell us about why you think this solution is the winner.
It's great to be among such august company. Going to talk about something quite different, not laser-based, but using LEDs that I think really solve some of the problems we've been struggling with. Maybe the next slide. So we've discussed in depth how AI clusters and generally ICs have a copper problem. And I think Katharine alluded to this picture in her presentation, where the NVIDIA system has 5,000 copper cables. And these cables are sucking enormous amounts of power, and they limit the number of GPUs that can go around the switch. Jensen famously in his speech declared very proudly that he's not using optics, and he's very happy about not using optics. And the factors that were mentioned was that the optics is unreliable, it's expensive, it's bulky, and it consumes a lot of power. So it's stuck to copper, but issue with copper is that you just can't put more GPUs around that switch. This copper problem extends everywhere. I think we all know how processing power in chips has increased because of Moore's law, but I/O really hasn't. Moore's law hasn't done much for the resistance of copper or the capacitance of free space. Maybe next slide. Okay, so we think that the problem is the fiber optics that we're using is really derived from technology that was developed for long haul links. So this is fiber optics, lasers, and single mode fiber are great if you want to go across the oceans, if you want to go across the continent. But if you want to go to the grocery store, go inside the rack, or go a few meters, it's the wrong technology. So using that technology that was developed fundamentally for long distances and applying it for short distances means you've got a lot of pain points you have to get over. Just a simple example, the wavelengths that we choose, 1.55 microns or 1.3 microns, that's the glass minimum loss and glass minimum dispersion wavelengths. We use those because we want the signals to go far. Well, if you're going a short distance, you don't really care that the loss is a quarter dB per kilometer, right? You can tolerate to have more loss. So we'd like to talk about a different approach that can address those problems. So next slide. And instead of piggybacking off the fiber optics world, we're instead piggybacking from the display world. It turns out that people as smart as us have been working in a whole different area, which is displays. And a technology has been developed for putting millions of LEDs on silicon chips. Apple was going to use this micro LED display for watches. I think they recently actually canceled that program, sticking with OLEDs. But all the big players are looking at these types of displays for virtual reality, for glasses. They're actually in production for car headlights. There's a picture of that sort of in the middle, and you can see all these teeny little LEDs, gallium nitride LEDs on silicon chips. There was one company in the area here, Mojo, that had a 100,000 pixel display. They put in a contact lens. So the maturity of this technology and what it's capable of is amazing. Now, normally people don't think about using LEDs for communications, fundamentally because traditionally LEDs have been slow. You can't turn them on and off very fast. You're relying on spontaneous emission versus stimulated emission. However, it turns out, next slide, that the gallium nitride LEDs that are used for displays can be tweaked to run extremely fast. Fundamentally, this is because electrons and holes in gallium nitride really like each other. And you can use that to make a very efficient LED, or you can use the same behavior to make a very fast LED. I think this was about a year ago. We did a live demo of our LED link at a conference, and we were modulating this LED on and off at 14 gigabits per second. And we put arrays of these LEDs, that's the lower picture, on silicon chips. And when you have arrays of hundreds, thousands, possibly even millions of LEDs, all modulating at these speeds, you can see that the overall bandwidth can be incredible. I think one of the presenters mentioned how clock speeds on chips hasn't changed in decades, and the chips themselves move data at relatively slow rates. These LEDs are very compatible with these types of speeds, and they can scale to the kind of numbers that you need to get data on and off chips. The picture down below is our little demo chip, and sometimes there's a video that plays. I don't know if this one does, but the LEDs turn on and off, and they send data in and out of that chip. So this was a 16 nanometer TSMC chip. It had 300 LEDs. Each LED was running about 3 to 4 gigabits per second, so sending about a terabit of data, and doing it at about a picojoule per bit. The advantage of using LEDs versus lasers is tremendous. In a laser, you need to drive enough current to get it over threshold. Just like an airplane, you got to get it airborne first before anything happens. LEDs, there's no threshold. You're moving around on the ground. You don't care about having isolators if there's feedback into the laser. There's really no polarization issues. There's really no modes to speak of. Frequently with lasers, we have to be very careful to AR code everything and pay attention to our coupling, because you can get bit error rate floors. And this really comes because you're talking about a narrow line with very long coherence length. Basically, it's speckle. With LEDs, there is no speckle. So you don't get these types of bit error rate floors. These LEDs can work great at high temperatures. I think recently, some friends of ours published a paper on our devices, and they took it up to 400 degrees C operation. So your silicon is going to die before your gallium nitride LED dies. We have extremely good reliability, incredibly low cost. These millions of LED displays are selling for tens of dollars. So the cost of the LEDs is extremely low. As you know, gallium nitride is used in LED lighting. Humanity makes almost square miles of the stuff. So the cost of the dies are very, very low. And as I mentioned, you can have massive parallelism. So there's no SerDes. There was quite a bit in this panel about the fibers. Unfortunately, I don't have a slide on the fibers, but we're not using standard Fuselica fibers that are quite expensive. And again, are really optimized for super low loss. The fibers we're using are fibers, borosilicate fibers from lamp fixtures. So these are used in lighting applications. They typically come in bundles of about 4,000, and they're used in things like microscope lights and sometimes in aircraft or pool lights. So we use those types of fibers. We bundle them up. In this case, it's a bundle of 300, but you can make bundles of thousands. And the diameter control is accurate, so you can put them in the right position, so you can make simple connectors and cables, and we have all of those things within the company. Let's go to the next slide, maybe. This is the 1 terabit demo chip that we showed at the Optical Fiber Conference. The 2 hexagons here are the transmitters and the receivers. So the right-hand hexagon is 330 LEDs. It's basically a little TV, but it has a frame rate of about 3 to 4 gigabits per second. So 3 billion frames a second versus 60 frames a second. The other side of it is the camera. In this case, we didn't yet have access to camera technology from TSMC and the other foundries. So we actually made our own little camera. It's an array of 300 silicon photo detectors made on a separate chip. And we turned it upside down and bonded on top of the main TSMC chip. In some processes, you can make the detectors in the chip itself. In this particular process, we couldn't figure out how to do that. So we have a separate photo detecting layer stuck on top of it. We use blue light, and blue light is absorbed very easily in silicon, so you can make very efficient, high-speed, low capacitance per unit area types of detectors that are easy to couple to and can be amplified with very low energy. This chip had a lot of functions in it. It had its own BERT and PPG and an eye monitor, and it's a pretty cool chip. Next slide, maybe. Where are we going with this technology? It's that co-packaged optics idea that Katharine mentioned again in the beginning of the presentation, and I think other guys have referred to. This is an implementation of our technology as a chiplet, where we make a 12 terabit chiplet, and you can see we can fit it into a 5 millimeter shoreline. In this case, we're going to be using a UCIe interface. So the shoreline density is actually limited by the UCIe. And we doubled the speed of our LEDs from 4 gig to 8 gig. As you've seen, we've gone up to 14 gig in the past. And we connect a larger array of fibers onto this device. So that's where we think the technology is going to go, from the demo chip to a co-packaged optics. And then what's really exciting about this is you can put these LEDs and detectors really on any chip. It doesn't even have to be a separate chiplet. It could go on the GPU ultimately, or on the memory. HBM usually has an active chip under the memory stack, so you could go into that active chip underneath and be able to connect directly to the bus that's running on the GPU and eliminate the SerDes. Maybe next slide. So just to summarize, people have dreamt about putting optics on chips for years. People complaining that silicon doesn't give off light. Well, if you put little micro LEDs on silicon, then obviously silicon does give off light. And you can make very large arrays of these LEDs. This technology is no good for long distances. This is not a technology you want to drive across the country. But it's fantastic for centimeters to meter type scale. It's simple, it's low cost, it goes on any silicon node, reliable, gives you the wide buses, and it's a right solution to Jensen's problem of all those 5,000 copper wires. Thank you.
Thank you very much, Bardia. That was a very interesting discussion, quite different to what we've heard from the other speakers. Maybe if I can just ask you one really quick question. So you heard Alan ask about upgradability and particular adding new fiber. And you've made a point here that this is a very short distance. So does that give you another degree of freedom? How would you upgrade to double your fiber or double your bandwidth?
Yeah, So you can obviously increase the bandwidth by increasing the speed of the LEDs. Our first demo chips are at 4 gig. We're going to go to 8 gig. That we use the same fibers. But frankly, when the fibers are relatively short and they're relatively inexpensive, it's not that hard to replace that fiber. Currently, we have 50 micron diameter fibers, which sets the spacing of the LEDs. These fibers also come in at 25 micron diameter, and you can even go down to 15. And if you multiply those out, go to 10 gig per LED and go to 15 micron diameter fibers of spacing, you're at almost 10 terabits per millimeter squared. So very, very high densities are achievable with this technology. And of course, the number of LEDs is almost unlimited. You know, displays run on millions of LEDs.
Yeah. Well, thank you very much.
So we're only limited by the patience of our audience, and I'd say we can certainly take 20 minutes if we have questions to fill that, and then we'll see how it goes.
Excellent. And I'd like to suggest Dan Pitt and I prepared a little poll for the audience, and I'm thinking maybe we start that now, and we have the audience think about how they would vote. So the question, Dan, I can launch this from here, I think. I thought I could. Polls and quizzes. It's Dan's poll. I'm launching it.
That's it.
Okay, and so the audience should be able to see it. On my screen, it's a pop-up that came up, and you are able to vote. And I see real-time voting happening as we watch. This is amazing. So we'll let this run for a few minutes here while we ask questions. So I'd like the audience to answer the question, what's the best way to scale? Is it wavelength, fiber, or are you undecided? And within the undecided, there's probably it depends, because there's probably some it depends as well. Let's see how this goes. And maybe we'll let it run for a little while, see if we are still adding votes, and ask some questions. So I'd like to get a sense for how much can we scale? What's the biggest bandwidth that we can do by either of these approaches? So Bardia, you just shared that you could do 12T terabits per second. I heard Alan say 32 wavelengths. And maybe we try and get this all in the same units. I think terabits per second is probably a common language for both approaches. So if Bardia has started the bidding at 12T, then what is the bandwidth using wavelengths? How much would be practical to put if you've got 32 wavelengths? And Alan,
I assume that was a question directed at me. So
yes, go for it.
So breakout fibers are running at 200 gig per lambda today. So there's lots of room to go. And our roadmap, we see basically headroom up to 4 terabits per fiber using 32 wavelengths. So plenty of room from where we are today.
So I heard 4 terabits.
Yes.
Per fiber.
That's
To
correct.
the denominator here. Terabits per millimeter or terabits per something, right? Because obviously you can scale into whatever you want with big area.
This is going to get very complicated. I was actually just thinking of not doing it per millimeter, but just doing, what's the bandwidth? So terabits per second. But you're right, size is important. So, it's got to fit together with the chip, probably in a relatively limited space. Shoreline density is always limited. So Bardia, you have kind of a special case with the fiber there because you're using illumination fiber. How about one of the panelists who is more focused on single mode fiber solutions and putting multiple fibers, maybe either Peter or Rebecca. Peter, do you have an opinion about how many fibers you could do?
So I mean, as Dan also mentioned, it's all a yield question. So how much can you yield on your solution? 16 full duplex channels is a good choice. 32, okay, and 32 times 200 gig, that gives you your 12.8 terabits per module. TX plus RX, counting TX plus RX as is typical in this community as well. So that's totally doable.
So what was the number you said?
12.8 tera.
12.8. Okay. Rebecca.
Yeah, I mean, I agree to first order what Peter said. I think the way to look at it is how is technology scaling for things like switches and XPU needs, and do we match the density of their shoreline off the die that they could get? And if you can do that, then you're good, right? So 12.8 terabits is great, but without a number to scale that by in millimeter shoreline, it's actually relatively meaningless. So I would look at technologies that are pushing those boundaries. So things like the switch technology is pushing those boundaries pretty dramatically, where you have, something like 512 IO out of the entire perimeter of the chip, right? So 128 IO out of a reticle edge. That is the density that you need to get toward, and ensuring that you have a pathway to scale with that technology is what's important.
Thank you. I'm going to ask some more of you for this, see if there's any more bidding on how many terabits per second we can get to here. But just to clarify, somebody has asked me in the poll that we're voting on, why wasn't there an option of both? Just trying to keep things simple. So I think both would be undecided, because it could be either. So undecided, either or, both, it depends, all of that's all undecided. I'm looking for, clear, strong opinions for one or the other.
In our case, Katharine, it's an and both for our existing demo technology as well as our roadmap. So we are working towards a 16T solution each direction, sticking with 8 fibers per direction, doubling the wavelength count to 16, upping the data rate, and also looking at the modulation format.
Okay, so did I hear a number?
16T per direction.
16T. Okay, thank you. I'm looking for some bidding. So Dan Kuchta, I see you grinning. Would you like to? You've been around the block a few times with this question. So where is your vote, and what do you think?
Well, I mean, if we looked at the cost of optical interconnect and cost where the whole solution, if we had the same data rate for the whole solution, the multimode fiber VCSEL-based stuff tends to come out cheaper, but it doesn't come out ahead in highest bits per fiber. So I think you guys know where the number is. It's like sub 1 terabit per fiber, but I still think that it has a tremendous opportunity to be the lowest cost solution in that regard. If you pick a solution, I think we can find a multimode VCSEL based solution to it that's lowest cost.
Interesting. So just to be clear, if your vote is for multi-fiber solutions, then how many VCSELs could you put together? How many fibers would that be? What's practical, and then what does that get you to in terms of terabits? I think traditionally it was 12 in each direction for the VCSEL solution.
Yeah, 12. I think what we were doing, 16 or 32. I made the case for, I think, going beyond 16 fibers in a connector, or well, the MT24s are actually higher yield than 16s right now, but that may be a historical thing, and I would be reluctant to go past 32. I just think it's going to be too costly. I mean, there's a whole aspect of high count fibers, if fibers in general, that I didn't bring up, but I think, Katharine, as a former data center operator, and your colleague Jeff Cox would say the connectors are the biggest problem, and it's not even that they have low loss, it's that people plug them in upside down sometimes and break them. They get dirty. I think you just don't want high fiber count in a connector. You don't want it to, they're harder to clean. There's all sorts of reasons. So I would sort of probably put a limit for both multi-mode and single mode at 32, although I don't like limits because somebody's going to come along and with a smaller connector or automate something. I think as soon as it gets automated, that changes probably our whole view on these channel counts. But at the time being, in the near future, that's where I would sort of put things.
Yeah, you're raising some very good points. There's some real world situations to do with just running things operationally and infrastructure. Rebecca, you look like you had something you wanted to say there.
Yeah, so as someone who has spent 8 years at Corning, I think I have a little bit of knowledge on fiber and fiber connectors, and absolutely what Dan said, there are challenges that hyperscalers see in the field in deployment with fiber connectors. Absolutely true. I do want to distinguish between the connectors that we're talking about, though, right? When we go into AI systems and we're talking about co-packaged optics type solutions, we are inherently talking about bringing fiber into the box and having connections that are only made during the creation of the box, right? And that's a different use case, a different reliability in terms of the number of connections, disconnections, the type of technicians that are doing it, whether automation can enable those connections to actually happen. That I think changes the dynamic within the box and changes the discussion within the box than one that would be at the front panel. So just something to think about there.
So you touched on something related to co-packaged optics, which I've been advocating for a while, which is the notion of field replaceability is a bit of a farce because the assembly of the box requires higher skill. And even though things are put together once, it also requires higher skill to take them apart when they need replacing. And I think you're kind of alluding to that, and I agree. I agree with that aspect. That's something we need to keep our eye on. And I think Amit also said he feels that the connector is probably the least reliable thing in the link. So we have to keep our focus on that as well, assuming you have reliable lasers.
I think this is really a key point. The application we're addressing is really different than standard fiber optic applications, right? We're talking about short distances again, where the fiber is maybe permanently attached. We need much higher reliability because field replacement is impossible if it's co-packaged or board mounted, as Dan pointed out. But it really does allow you to use new things that you couldn't do before. So we shouldn't be wedded to standard types of technologies that were really designed for other applications.
Yeah, I think that's certainly true in some of these new diverging markets, maybe in the front end, that there's enough single mode fiber out there. We may end up with different solutions. How interesting. Anyone else got some more on this topic? Otherwise, I have some other themes from the questions. Cost and power are coming up in as topics, and Rob in the chat has expressed this question a couple of different ways, but he's asking each of the panelists basically to pull holes in the other's solutions. What do each of you see as the big disadvantage for doing it the other way, right? And so and then he's called out power and cost as two of the things that are top of his mind. I have a whole load others, but so Dan, you mentioned a little bit about cost.
Yeah, I'd like to go first. I'd be more than happy to pick apart each of my fellow panelists' solutions once they hand me their bill of materials and component costs, because I have no idea what each of them cost right now. I don't even know how to rank them in order of cost.
Okay.
So if you had to take an educated guess, what would it be right now?
What would it? Well, Alan, you're selling lasers, right? So I'm going to give you, you're the lowest cost just because you're a component vendor, right?
Lasers and interconnects. We'll do both.
And you know, Peter and Amit are similar technologies. I probably want to put Peter next because he's a small business that's hungry for customers, and so he's going to be aggressive. Then Amit, and then honestly, Rebecca, I wasn't clear on what your solution was. So I don't know where to put you. I'm sorry. Don't.
All good, and by design, right? We are
Okay.
a new startup. There's a lot I cannot say publicly as to what we're doing.
Okay.
But maybe to answer the question a little bit more generically, one of the things that I would say you're looking at when you're driving to AI is also an opportunity cost. So if you can't scale to the volume that AI can scale to, then your solution is costing the customer more in the end, even if your individual component costs less than a cent. If you can't scale to the volume, you've missed out on a huge revenue opportunity, and the customer cannot deploy, which is a huge cost to the customer. So if they're going to bet on you, they need to bet on something that can scale to that volume, which I think is really important. One of the challenges I see with more wavelengths is there's not a proliferation of sources that can be used for high power to enable the solution. And no offense to our fellow speaker, Alan, but pretty much all of the multi-wavelength sources, aside from Amit, are startups. And, if you look at that as a solution space to work within, then it becomes very hard to bet on a solution and know that it will scale, especially when it's so material dependent. And history tells us that materials take a long time to get to full reliability and volume requirements. So that's where I would see a large challenge in scaling. And as much as Amit loves his laser technology, it's not available to everyone.
I think Rebecca just invited me to segue into your question about manufacturing and ramping, Katharine. But quick comment. So on the topic of high power, I think that's actually the wrong direction to go for lasers, because laser reliability actually scales as 1/current to the 4th power or 3rd. So using high power lasers and splitting isn't the optimal direction for system level reliability. And I think the general direction that the industry is going in terms of using more and more higher power lasers for DR4, DR8 splitting isn't necessarily the best approach in my mind, because again, of that reliability, you're literally going the opposite direction of where lasers are more reliable, which is lower power and lower currents. And also, if you knock out that one laser goes down, all 4 or 8 lanes go down. So the blast radius is quite high. And so the use case for us with comb lasers isn't to try to put out a very high power from the laser itself because of that reliability consideration. But there's other ways you can compensate for that in the link itself. And then on the topic of manufacturability, I think Rebecca brought up great points. It's laser material and reliability takes time. We've been working on that either directly at Quintessent or indirectly at UCSB for the better part of a decade now. And so we feel pretty good about the material supply chain. We have multiple partners for the quantum dot epi that we believe we can go to volume with. And we understand the physics of the reliability and failure mechanisms pretty well. So at least for Quintessence, we feel pretty good about the concerns that were brought up.
Yeah, I think I like to build on Alan's point. Traditionally, there's been two reasons to go to very high power lasers. One, I think Bardia mentioned, is the threshold penalty. You don't get it to laze. So when you go to a shared laser, you pay the threshold penalty once for as many channels as you're driving. The second is, the cost of a laser and everything that goes into it. And typically the power is not scaling with area, but the cost is scaling with area. So So I think that's been the traditional reason. But in some of the new approaches with QD lasers, in our particular case, we have a certain size indium phosphide coupon we can get on there. And so, multi-lambda for us comes pretty cheap. It's not equal to the cost of adding a separate laser. In terms of the power and how you address the link budgets, another thing that we like to use selectively and inventively is SOAs, right? You don't need all the power coming out of your source that you need to close the link. So how you use SOAs in the mix also makes the overall solution architecture very interesting.
Yeah, so it's a great discussion. I think we could go on doing this all evening, but it looks like the poll has converged. So I think we have a result, and I was expecting it to be much closer than this. It looks like we actually have 43% of the voters voted for Wavelength. Alan, that's despite you being hugely outnumbered, I feel. But
the underdog wins.
19% voted for fiber, but there is a very large contingent that's still undecided. So whether that's all those other catch things in there, whether it's both or maybe, or it depends, or one first then the other, who knows? I think there's still plenty to discuss here. So thank you very much. I'm going to stop sharing the poll now. And I'm looking at Dan. I'm wondering how much of this sort of grace extra time do you think we can really borrow here, Dan? Can't hear you.
As long as the evidence doesn't disappear, you can go a little longer.
Should we do some more of this?
I'd say let's do one more question. Yeah.
Oh, question. Okay. I get to pick because I don't see any more questions here, but how could you possibly, we were talking about radix a lot, so this is an odd question. I'm going to ask Rebecca, since you talked a lot about radix, how would this work with optical switching, right? We have optical switching hasn't happened except Google, right? And Google's special in a lot of ways, but I hear optical switching being talked about. There's a limited number of MEMS mirrors that can move data around in that switch. It's a bit of a special case. But how would you do that if you had lots of parallel fiber or lots of different fibers going around? How would that work?
Maybe to answer this in a different way, just because I can't divulge some of the stuff we are working on, but what not to do, right? So one of the biggest challenges with optical circuit switching is the loss. So if you take loss into account, you say, let's say you had a DR link, you're now penalizing yourself in that DR link, right? You're taking away some of the connections that you would have normally been able to do in order to support the solution. So you have to be very focused then when you deploy the system of meeting the link budget required, which makes that sort of optical circuit switching very, very challenging, right? Yeah. I think Google's solution is something like 3 dB link loss, and a DR link budget's 4 dB, right? So they're pushing the transceiver vendors on either end to have a slightly larger link budget than the DR spec in order to compensate. They're also making both directions go on the same fiber and having to have recirculators to pull out each direction and separate them, which adds to back reflection tolerance challenges, all to get around the fact that you can't put so many little mirrors in a place at a given time, right? So definitely, I think, a challenge to use that technology and scale. If you take optical circuit switching on silicon specifically, there's a lot of challenge there because you want to use single mode technology. And single mode technology means that you have both polarizations entering your silicon, And now you have to figure out how to do circuit switching with both polarizations, which adds to loss because you need to either figure out how to put those polarizations back to a single polarization without causing noise to your signal. Or you have to have two separate, completely separate circuits operating independently, which adds to the size of the device and the power of the device, which doesn't make any sense. So right there, you're probably at a loss that's even higher than the 3 dB loss that I just mentioned Google has, because not only do you have to deal with the polarization rotation, but every single one of those little itsy bitsy circuit switches that you want to put in there to make a non-blocking solution is adding 0.1 dB, 0.2 dB, and so forth. That adds up dramatically into that solution, really heavily hitting onto the overall link budget that you have and the power that you would need in a laser to compensate for it. So I definitely think those are very challenging solutions that you need to address in a completely different way that unfortunately I can't discuss here. But you know, these are compounded if you also add wavelength into the mix, right? Even further, if you do those in a traditional optical circuit switching method.
But there is one other circuit switch that you didn't mention, Rebecca, which is the simple, I call it low tech but efficient tech, the fiber robot that just
sure. I considered mentioning that
which is actually not that bad, because what the optical circuit switch is really an automated patch panel. It's not like a circuit switch in the Sonnet.
Yes.
It's an automated patch panel. And for that, speed doesn't matter all that much. And once you start talking about connecting fibers, you can connect empty ferrules. That's fine. Then you have, with the exact same complexity and loss, you all of a sudden connected 32 fibers to each other.
Yeah, so I would say at that point, right, you're talking about space in the data center, right? Because it is relatively large, right? It's a kind of a full rack type solution. And whether or not you can fit it in the data center footprint, or you'd rather use that for GPU, is there a better solution you can get even denser on? But yeah, I would agree with you that it adds just a connection point.
Yeah,
in that sense.
Well, it was kind of an off-the-wall question. I wasn't expecting any of you to have prepared for that one. So thank you very much for being such huge sports. This was a lot of fun. I would like to thank each of you for joining. This has been wonderful. And thank you for really getting into it and you know, sharing all the details and the nitty-gritty of why this is or isn't the right way to do it. And I think, let's see, there's not much else to say except thank you very much. I think you moved a lot of the audience, which is very interesting. And Dan, over to you. I think there's one more final thing to say, right?
There is. First of all, I want to thank you, Katharine, for agreeing to moderate the session, doing a spectacular job pulling it together and running it. This is the best panel I think we've had in 20 years. Or 25, and I'm just thrilled with the inventive people we have on the panel, and you know, every one of you has brought really new thinking into my world. And of course, you know, I've known most of you for a while, and I am excited by the future of optical technology, especially in the data center, and to accelerate AI. I didn't vote because I'm not allowed to, and I kind of liked what Alan said, which is you've got the fibers there. Let's add to the wavelengths first. But I also think with some of the new fiber multiplexing and parallel technologies coming out, and especially perhaps with low-cost LEDs, we're going to see more opportunities to do that in parallel. And the data center challenges are so different from the long-haul telecom challenges that I think it's right for some new kinds of approaches to using optics. So my final word is, well, first of all, we have another great day starting tomorrow at 9 o'clock. But how did Interconnect started in, I think, 1993. I've been involved since a year or two after that. And we always met in person on the Stanford campus until 2008. And then we moved to New York for 1 year. And then we came back to the Bay Area. And instead of being at Stanford, we were at companies. The reason we went to New York, and by the way, well, this is hard to tell this in the right sequence. we used to have sometimes dinner before the panel discussion or the cocktail reception before the panel discussion, in which case the panel got really interesting. But we always concluded the first day with some kind of a cocktail period and a cocktail hour. So in 2009, we went to New York and we're hosted by Credit Suisse. And the reason for that is because we had a couple of attendees from Credit Suisse and one from the New York Stock Exchange that would come to our conference every year at Stanford. And one in particular sat in the back and didn't say too much, but whenever he spoke, it was like, oh boy, we didn't think of that. His name was Head Bubba, or the Head Bubba. That was his legal name. It was not the name his parents gave him at birth, but it became his legal name. And I actually have a photograph of him. Not a great one. He didn't look like we normally expect the vice president of IT at a major Swiss bank, Credit Suisse, to look. But that was him. And he brought a lot of reality to our discussions and said, you know, I'm running a bank here. This is what's important to me. And you're talking in theory or whatever wasn't relevant. And so we listened to him, and then he hosted us, and we were very grateful. And then we came back here, and he was a very generous guy. He shared things with us. He had certain hobbies and interests, but he was very generous and very kind. He died in 2013 of a medical problem. And since then, we have been memorializing him at the cocktail reception right after or before the panel. Well, since 2020, we haven't been in person, but we don't want to let this opportunity go to waste to thank him for his friendship and to remember him. And so here I happen to have handy, I should probably turn off the virtual background, a fine glass of California Zinfandel. I'd like to make a toast to the memory of the contributions and the kindness of the Head Baba.
Cheers.
And with that, we shall end the day's program. Look forward to a great one tomorrow. And thank you all for the best panel in just about living memory.
Thank you, everyone.
Thank you, Dan and Katharine.
And thanks all to the audience who stuck around for a long time.
Bye-bye.